Hello, I'm Jack. Welcome to Practical Programming channel. In this video series, you will learn everything you need to get started with WebGPU Graphics Programming. The examples discussed in my video series so far will apply a fixed color by assigning a desired color value to the flag color variable in the fragment shader. In this video, I will explain how to use the color map to render 3D surfaces. Surfaces play an important role in various applications, including computer graphics, games, and 3D data visualization. In some graphics and chart applications, we need a custom color map to achieve special visual effects. In fact, the color map is just a table or list of colors that are organized in some desired fashion. We can create a custom color map with an M/3 color matrix with each row representing RGB color. The row index can represent the Y data of a 2D chart or height of a 3D surface plot. For a given color map matrix, the color data value can be linearly scaled to the color map. Here, we will use the Git tool to clone the source code used in the last video. Here is the download link at the GitHub repository. From this link, you can download the source code used in the last video. Now open a command prompt window and run the following command: git clone, and paste this link. This will generate a WebGPU 22 folder on your local machine. This folder contains the source code used in the last video. Now we want to change the name of the WebGPU 22 folder to GPU 23. Rename WebGPU 23 and cd into it. At this point, we are going to start Visual Studio Code with the command code period. This is a Visual Studio Code interface. Okay, we can close this welcome page. Now here contains all the source code used in the last video. We can easily create a custom color map using simple mathematical formula. Here, I will provide several commonly used color maps using various M/3 color map array. From the src folder, we add a new TypeScript file called colormap.data.ts. Now add the following code to this file. This code contains a new function called colormap.data. Inside this function, you can see each color map contains 11 RGB color arrays. Here, this small window shows the color strip generated using these color map arrays. You can see that each color map has a familiar color map name, such as H, SV, Heart, and Jet. This color map strip corresponding with the color map data here. In the color map data function, we assume that those 11 color arrays are uniformly distributed in the range of 0 and 1. For example, the color 0 represents a color at 0, while color 5, 1, 2, 3, color 5 represents the color at 0.5, etc. However, we have to use the interpolation methods to get a color at 0.55 or any other arbitrary locations, because we only assign color at 0, 0.1, 0.2, 0.3, and so on. Here, we will use an npm package called interpolate arrays to do the color interpolation. Now open a new terminal window. and run the npm install interpolate array to install this npm package. Okay, finished. Now we can close this terminal. Now at the top of Colormap data.ts file, we introduce this package with the require command const interpol equal require interpol. You can see here we use require instead of import. In the previous video, I explained why we use the require, so I don't explain it further here. Next, we need to add a new function called add color to this file. This function accepts the x argument whose value is in the range of min and max range. It allows you to interpolate a color for an arbitrary x value. Inside this function, we first get a color array by calling the Colormap data function with the color map name, and then we make sure the x parameter is in the min and max range. Next, we normalize the x to the range of 0 and 1. Finally, we interpolate the color of the x for the x value by calling the interp function from the interpolate arrays package. This add colors function returns RGB array with each component be in the range of 0 and 1. So now we can save this file. Next, we rename the light.ts file here. We call the surface.ts file. This is a common file that will be used to create various surface plots. First, we need to change the function name from create shape with light to create surface with Colormap. And then we need to add a color data as its input argument. Here we have vertex data and normal data, but we also need to add color data here. Inside the pipeline here, we have our buffers attribute. Here is position data, here is normal vector data. Now we need to add the color data here. Copy this. Here we change the shader location for the vertex is 0, for the normal data is 1. Now for the color data, we need to change this shader location to 2. The code for the uniform data and rotation and camera, as well as uniform buffer and layout, all this code is the same as that I used in the last video, so we don't need to change anything here. The only thing we need to change is that we should add the color buffer to the render path here. You can see here we have vertex buffer and normal buffer. We also need to add the color buffer. And path set vertex buffer. Here is 2 color buffer. Oh, sorry, here we need to add the color buffer here first. We have vertex buffer, normal buffer. We also need to add a color buffer for the color buffer using color data. Okay, so here we add a color buffer to the render path. Now we finish the modification to this file. Now we can save this file. Next, we need to make some changes to the shader code because we want to incorporate lighting and color map into the shader. In addition, we need to apply light to both sides of a 3D surface, since most surfaces are not closed 3D object. From the SRC folder, open shaders.ts file. Now we need to replace its content with the code This shader is very similar to that used in the last few videos, except that in the light inputs here, we replace the object color by the is two-side lighting parameter. Inside the vertex shader, in addition to the vertex position and the normal vector, we also add the color data here. Here we set the location as 2 because in the surface.ts file, we define the shader location to 2 for the color buffer. Within this main function, here we process the color and put the output to the V color here, this V color. In the fragment shader, we use the processed color data as our object primary color to obtain the final color. You can see here, we use the V color as object primary color because ambient and diffusion is the primary color for our object. Inside this main function, we use is two-side lighting parameter that control whether lighting is applied to one side or two sides of our surface. Here, if setting the two sides equal to 1, which is also default setting for the two-side lighting, while if set to something else, for example to 0, is for one-side lighting. For two-side lighting, we apply lighting to the back face side by adding the light with reversed normal vector. You can see here for the diffuse. This is for the one side. We have dot N and L. If it's two sides, we need to add another term by reverse the N. But here is minus N dot L. This is lighting for the back side. Same thing for the specular light. For example, here is N dot H, the half angle vector. If it is two sides, we need to add this term. We just reverse this N here, minus N and H. So we add the back side, the light, by reverse the normal vector, the sign. Now we finish the modification to this file. Now we can save this file. Since the Colormap model with lighting in WebGPU looks very involved, so I will stop here for today. In next video, I will show you how to use the Colormap model to build 3D simple surfaces in WebGPU. Most examples presented in this video series are based on my recently published book, Practical WebGPU Graphics. From this link, drsu.net.com, you can see the details about this book. I have created a GitHub repository to host the source code used in this video series. From this link, you can download the source code used in this video series. I also created a live demo at this link. This demo shows the live results by running the example projects presented in this video series. I will end this video here. See you next time. Bye.